Let us study the variation of the conductivity and molar conductance with concentration. Now this variation was studied in detail by three scientists, Debye, Huckel and Onsager, and they together gave an equation which is called DHO equation. Now the equation is like this, that the molar conductance at any concentration is equal to molar conductance at infinite dilution minus A under root C. This is what the equation is. I am repeating again, this one is molar conductance at concentration C. This lambda naught is molar conductance at infinite dilution. A is a constant which depends on the nature of the electrolyte, basically on the charges of the ions which they give out. And remember, same type of the electrolytes or the salts which we are taking will have a same type of value, A value. Like if we have NaCl, KCl, these are called 1,1 type of charges because they have 1,1 type of salt because they have charges of +1, -1, +1, -1, and they will have a same value of the A. Like the salts like MgCl2 will have a charge 2,1. They are called 2,1 type of salts because they have 2+ and -1 charges. So like this. So A is a constant which depends on the nature of the electrolyte, and C is of course is our concentration. So this is what is an equation. How it comes, we are not bothered. The reason is because we have only the qualitative study of this equation, what interpretation we can draw from this equation. We don't have any numericals on this equation. So it's called DHO equation, Debye, Huckel and Onsager equation. Now when we compare this equation with y equals to mx plus c, which is an equation of a straight line, we can plot a graph to study the variation of the kappa conductivity and lambda molar conductance with concentration. Now let us see how this graph is drawn. Now the equation we know is molar conductance is equal at any concentration is equal to molar conductance at infinite dilution minus A under root C. Now we will compare this with y equals to mx plus c. So we can draw a graph which is almost like this. In this, the y will be your when we compare this with y equals to mx plus c, we can have y as your molar conductance along y axis, and your x is your under root c. Now what we get is, we take two examples. The first example we take is of a strong electrolyte, like we can have 10 ml of 1 molar KCl. Now in this, let us find that this KCl is having at 1 molar concentration this much of molar conductance. What we did is we started adding the water to this. We added 10 ml of water so that we are diluting it, we are decreasing the concentration. So when we added 10 ml of water to this, the concentration got decreased and we determined its molar conductance. We again added 10 ml of water, we again determined its molar conductance. And this is how we kept on adding the water and again, and after adding every time after adding the water we determined the molar conductance, and when we got the different points, we joined them and we got a graph which goes very straight, which can be extrapolated and can be determined that where it intercepts the y-axis, and the value or the place where it intercepts the y-axis is called molar conductance at infinite dilution. Now the graph, the slope is negative, which shows that the molar conductance increases with dilution. It is very clear from this graph. It decreases with dilution. What is the reason? Is because with dilution, interanic distance increases and the interanic interactions decreases. Ions are able to move more freely, and that is why their molar conductance increases. So lambda molar increases with dilution. This is most important. Why? I am repeating again, two reasons. Why? Because with dilution, volume is increasing, so interanic distance increases, interanic interactions decreases. That is why lambda increases. So this is the main feature. But what happens to the conductivity? Conductivity is again important to be known. So molar conductance increases with dilution, as I have explained it to you. But let us see now what happens to the conductivity. See, kappa decreases with dilution. Kappa decreases with dilution. Why? Because kappa is the conductance shown by the ions present in 1 ml, 1 cubic centimeter volume of the electrolyte. Now with dilution, the number of ions decreases in per ml of the electrolyte. They go more away from each other. That is why, since the number of ions in per ml of the electrolyte decreases, kappa decreases with dilution. But since kappa is multiplied by V to find out molar conductance, and V is the volume which is increasing by dilution, the overall lambda increases. So this is what we observe in case of a strong electrolyte, and what we find most interesting is that for any strong electrolyte, the maximum value of the molar conductance appears at infinite dilution, when the solute is almost, the electrolyte is almost as negligible in the amount. We have maximum dilution, and then at that point we call it as a lambda naught, which is called molar conductance at infinite dilution. This is also called the limiting molar conductance, because that's the end, that's the maximum value any salt can have. Now let us see the second case, second example, which is actually of a weak electrolyte. When we take a weak electrolyte, like we have taken like suppose we have taken 10 ml of 1 molar acetic acid. Now the same acetic acid will have 1 molar, at 1 molar concentration will have a far lesser molar conductance than the normal usual one, strong electrolyte. Why? Because it's a weak electrolyte. Weak electrolyte means what? Because it doesn't dissociate completely. So it's already, the molar conductance is lesser, is lesser value, is having a lower value, then that is why it is placed here. Now we started adding water to the same, in the same situation like we have been doing it with the strong electrolytes, so that we can decrease the concentration and we can find out what is happening to its molar conductance, and we start getting the points here, and when we join those points we got to know that the graph goes like this. So the graph in this case is showing a much steeper rise in its molar conductance than the strong. Of course, the first thing is the molar conductance of weak electrolytes also increases with dilution, as in the case of a strong electrolyte. The reason is same, because with the increase in the volume, with the decrease in the concentration, what is happening is the interanic interactions are decreasing, and the ions are able to move more freely, and that is why the molar conductance increases. But this increase is much more steeper than the strong electrolyte. The reason is because with dilution, we know the formula that alpha is equal to under root K upon C. What is, we know from the equilibrium of the class 11th that as the concentration decreases, the lambda alpha, which is called the degree of dissociation, increases. Now therefore what we find is with the dilution of the weak electrolytes, the degree of dissociation increases, so more of the number of more electrons, more ions actually are released from the same electrolyte, from the same weak electrolyte, and that is why, since more number of ions are released, alpha is increasing, the increase is much steeper. But due to this much steeper increase, this graph of this weak electrolyte doesn't crosses the y-axis. Therefore, we are never able to know the molar conductance at infinite dilution for the weak electrolytes. So we cannot find out experimentally the molar conductance of the weak electrolyte, because they doesn't dissociate completely, so we can't get their limiting factor, limiting value, and the graph doesn't crosses the y-axis. So we cannot get experimentally, we cannot obtain experimentally the molar conductance of the weak electrolytes. So this is how we study the variation of the conductivity and lambda molar conductance with concentration.